typical example of a zero order reaction, a reaction in which the reaction rate is independent of the concentration of the reagent, is blood alcohol levels, or the metabolism of alcohol. The enzymes get saturated, and the enzyme and transport carriers, the one that metabolize the alcohol, get saturated, and once they are saturated, they will break down alcohol in blood at a constant rate. And it doesn't matter what the concentration of the alcohol is, the rate of the reaction will not change. And that is what it shows here in this graph here. So once you reach saturation, the enzymes will break down the alcohol at a constant speed, and it doesn't matter what that initial concentration is, the speed will be the same, and it will not change throughout. So you have less and less alcohol, but the reaction as the enzymes do their work, but the reaction rate will not change. It will not slow down. It will still be the same rate. Let's have a look now at first order reactions. A first order reaction is a reaction in which the reaction rate doubles when the reactant is double. And the reaction rate for your equation that defines that equation is K, the constant that depends on each reaction and the temperature and the concentration of the reagent to the power of 1, the concentration of the reagent. And this is what we're trying to represent here. This is a curve of how a reaction that follows that first order, the reaction is directly proportional to the concentration of the reagent looks like. And have a look at what happens with the T half. The time it takes for the concentration to halve. So you start with a particular concentration, A sub 0, and this is how long it takes for the reaction to reach, for that amount of reagent to halve. And then if you start from here and say, okay, how long is it going to take for that reaction, for that amount of reagent to halve again? Well, you reach this point, and if you look at this T1/2, and then what would be for this amount of reagent to halve again? Well, then you have here, if you look at those those 3 T1/2, those times in which the reaction has halved the amount of reagent that you have in the reaction has halved, they are the same. It takes the same amount of time to halve the amount of reagent you have in the reaction. It doesn't matter how much reagent you've got. It will take you the same amount of time. It doesn't matter if you have a lot or towards the end when you have very little. The amount of time it takes you to halve that quantity is the same, independently of the concentration of the reagent. And I'm going to highlight this, but I'm going to show you why I'm highlighting this in the next slide. That what we call the integrated rate law, and why we need to use it. But in the next slide will make more sense. At the moment, let's just have a look at that equation. You have the logarithm on base E, that's what the ln means, of the concentration of the reagent at any particular time, equals minus kt, k a constant, t the time, plus the logarithm in base E of the initial concentration of that reagent. So keep that in mind, because I will tell you why we use this in a second. This is an example of a first order reaction used in medicine. It's the radioactive decay of iodine 131. Iodine 131 is one of the 2 isotopes commonly used in medicine. It's used for imaging, and it can be used in large quantities to treat some thyroid problems. So if you represent the concentration of iodine 131 versus time, there's an exponential decay. It's a radioactive decay. It produces xenon and an electron. And that's okay, that's a curve. This is the curve that we've got here. we chemists and in general scientists do not like curves because it makes it difficult. There's nothing like a straight line to be able to predict how things are going to happen, how to extrapolate, etc. So we try to transform any expression we have into, is there any way I could use this data and present it as a straight line? And you can, and that's what the integrated rate law means. If I take the equation I showed you before, but I adapt it to iodine 131, so you've got the concentration of iodine 131 at a particular moment in time, minus kT, plus, again, the log in base E of the initial concentration of iodine 131. Well, if you represent in the y-axis the logarithm in base E of concentration of iodine 131 versus time, that is a straight line. And this is what I have in the slide, in the image at the bottom. The time in the x-axis, log in base E of the concentration of iodine 131. And that's one of the ways that we know we can find out if a particular reaction is a first order reaction, because we will see that second order reaction gives us also curves and they look very similar, and it's very straightforward to see, oh, is this first order or second order? Representing the concentration versus time, something reacts. If it gives us a curve that is not particularly useful, doesn't tell us is it first order, because you will see that all the other reactions also have curves. But if you represent the log in base E of the concentration versus time, and you have a straight line, then you know that's an example of a first order reaction. Second order reaction, and apologies because this slide packs a lot of punch, but let's deconstruct it slowly. What is a second order reaction? With a second order reaction, this exponent needs to be 2. That's what the second order means. So how do you get that 2? Well, if you only have one reagent, then that means that the reaction rate depends on the square of that reagent. So when the amount of reagent A doubles, the rate will quadruple, that sort of relationship. But if you have a couple of reagents, then what it means is that it depends on each of them independently, not the square, but the square as the combination of both. The sum of the exponents of the reagents involved in that equation needs to add up to 2. And it might be because only one of them calls the shot, you only have one, or the others do not interfere in the reaction rate. And it's beyond the scope of these videos to explain why would that happen. We can have a chat about it if you want to. Or you have a couple of the reagents, and each of them is the rate depends on that one proportionally, but together the rate depends on the square of the concentration of both reagents together. So we have a look at how the concentration of A in a second order reaction changes. And it's also a curve, but it's a different curve. Let's have a look at what happens with the T1/2, the amount of time that takes for the concentration of your reagent to halve. If you look at the first one, so this is time and a half, this bit here. If you then look at the next time and a half, would be, from that one to how would be to halve that amount. Well, it's this one, and look, that is longer. And again, if you halve that quantity again, you have another time and a half, and it goes longer. It gets longer. Time and a half, the amount it takes you to halve the quantity of reagent you have in that moment in the reaction, increases steadily. It doesn't stay constant as with the first order reactions. The reaction gets slower as it progresses. It takes longer and longer to reduce the amount of reagent by half. And again, a look at this integrated rate law, which will come into play in the next slide. A typical example of a second order reaction is the decomposition of nitrogen dioxide. So nitrogen dioxide can decompose into nitrogen oxide, NO, and oxygen, dioxygen, molecular oxygen. And that is a second order reaction. Why do I know that? Because when I represent concentration of nitrogen dioxide versus time, well, it changes, doesn't stay the same, so it's not a zero order reaction. When I represent the log in base E of the concentration of nitrogen dioxide versus time, it doesn't give you a straight line. And that means that when I apply this, when I try to apply, I wonder if I can apply this equation, which is the equation for the first order reaction, minus KT plus log of the concentration of NO2 at the beginning. When I try to represent, okay, what if I represent the log in base E of the concentration of nitrogen dioxide versus time? Do I get a straight line? Well, the answer is no. It's not a straight line, it's a gentle curve. That reaction is not a first order reaction. However, if I represent, and where the integrated rate law comes into play, the one upon the concentration of nitrogen dioxide versus time, so using this equation, so the inverse of the concentration of nitrogen dioxide versus time, that gives me a straight line. That means that reaction is a second order reaction, and that's how I recognize them. So that's how we recognize them when we are doing chemistry. We will set up experiments in which we change the concentration of the reagent or reagents, depending on if you have one or more, with time. So we run several experiments and varying the concentration of the reagent and measure the rate of reaction, how fast is the concentration changing. And then we try to feed that data to the models we've got. Zero order, first order, second order. There are more orders, but we are going to start with the second order. They are the most common ones. And we see that which one fits into that straight line. And that tells us, oh, this is the reaction, this is a second order reaction. And that's what I'm saying, that rate laws are experimental. It's not something that just looking at the reaction, it's going to be first order or second order, or no, it has to do with the reaction, the way the reagents react, but it's not something you can spot just looking at the reaction. Just because there are a few twos here, they have nothing to do with these two. These two is experimentally determined. So this is important you keep that in mind. Just by looking at the reaction, you will not be able to know what order is going to be. You will need to get some data of concentration versus time and see how the concentration of the reagents change, and then do the graphs and see actually which order it is.